vessel again. We have an individual who all of a sudden has an increase in blood volume. Right? So they have an increase in blood volume. What should that do to their blood pressure, given what we just talked about? Because blood pressure is a type of hydrostatic pressure. What should happen to their blood pressure, up or down? It should go up. There are conditions where you volumize your circulatory system. Your heart starts to fail. You're in congestive heart failure. You will start to accumulate fluid within your circulatory system. Now you tell me what's going to happen to this individual. Should we get more or less filtration in this particular instance? More or less? We're going to get more, right? So we are going to go from that, which is normal over here. Let's just make the arrow bigger. Filtration. Capitalize the first letter if you want. Give yourself a visual. You're going to have lots of fluid in the interstitial space. Tell me what that's called again. Excess fluid, excess water in the interstitial space is called edema. This is another way you can get edema. Edema will happen in the first patient because they were starving. It's happening in this patient because they have high blood pressure. You get fluid build up in the lungs. You ever hear that? People with congestive heart failure get fluid build up in their lungs. This is how it happens. People with congestive heart failure, they'll start to get swelling in their legs. Anybody ever see that? It's because of high blood pressure. Blood starts to build up within the veins in their leg, and it just gets pushed out of the circulatory system into their interstitial space. This is how it happens. Okay? Are we good? Yes? Okay. So that's filtration. That's what I want to talk about with filtration. Now let's move forward. Now, we just drew this. This is what we just drew. Now, that's not what we just drew, but we drew this one right here. Is this picture. All right? But I added something to it. All right? The osmosis part. All right? Now what? Last passive transport mechanism is facilitated diffusion. If you facilitate something, it means you help it. Facilitated diffusion is a passive transport mechanism that uses transporters in a membrane to move a molecule across the membrane. And in this particular picture, we're seeing a piece of a membrane, and we're seeing this transporter here take whatever molecule this is, it doesn't matter what it is, that could be a sodium ion, that can be a glucose molecule, that can be an amino acid, that's just something that needs to go from the outside of the cell to the inside of the cell. It can move the other direction as well, by the way. It can be moving inside the blood or out of the blood. It can be moving in the lymph or out of the lymph. In the interstitial fluid or out of the interstitial fluid, it doesn't matter. We know that things move in and out of all the compartments. That was the first picture that we drew. In this particular case, they have this molecule moving from point A to point B. Now I want you to notice something, that it's just not a door that opens. These transporters that we're going to be discussing, we're going to discuss a few, literally need to grab the molecule and either throw it into the cell, or out of the cell, or into the lymph, or out of the lymph. It needs to be grabbed and thrown. It's not a door that just opens. And the shape of the molecule has to be such that that's allowed to happen. And so we need what? It starts with an S. We've talked about this, where shape matters to something grabbing something. We need specificity. If the molecule is not specific for the transporter, just like when the molecule wasn't specific for the receptor can't grab it. So in this particular case, we have this molecule here, maybe it's sodium, and this is a sodium channel. You guys talked a little bit about channels with Siebert, I'm pretty sure you did. That sodium, it has the right shape, the sodium channel can grab it and throw it into the cell. Let's say that that's chloride. That ain't working through this particular sodium channel. Why? Because it's not the right shape. So how does chloride get into the cell? It needs to go to the chloride channel. There are sodium channels and chloride channels and potassium. There's all kinds of channels that are in the body. By the way, when these are drawn, there's only one receptor here. There's not just one of these receptors in the membranes of these cells. There are thousands of individual receptors, and there are thousands of different, transporters, and then there are many, hundreds and hundreds of different transporters. If you had to wrap your mind around what a cell is doing and what it has to do it, it doesn't even make sense that this little thing that's microscopic, that's about 20 microns big, can have so much stuff going on. And for it not to go wrong, too. I'll say that a lot over the next few semesters. The body is a beautiful thing. And how efficient it is, and how well it works, and how just one thing can go wrong, and now you've got problems the rest of your life, or bad stuff happens, but most often it just doesn't. And transporters are certainly one of those things. So when it comes to facilitated diffusion, we have molecules that can't simply squeeze through the membrane. What kind of molecules can simply squeeze through the membranes? Little teeny what kind of molecules? Very small lipid molecules, right? When did we learn that? We learned over here with simple diffusion, right? Those molecules don't need a transporter. The yellow ones don't. That's simple diffusion. These do. What kind of molecules need to be carried by a transporter? Ions, for example. Why? Because they have a charge. They can't squeeze through the membrane. They're not fat soluble. Glucose cannot squeeze through a membrane. It's not a lipid, it's a carb. It's very polar, right? We know that. We learned it's got a whole bunch of oxygens. Molecules that need to be carried through the membranes are ones that cannot simply squeeze through the membranes. All right? Like ions, like amino acids, like glucose. They need a transporter. Now, it might be a transporter that moves them passively. It might be an active transporter that we'll talk about shortly. But regardless of what kind of transporter we talk about, it all works the same way. The mechanism is the same. It needs to grab and throw, grab and throw. All right? One other thing that's important to discuss, and that's saturation. You can only ask these molecules to grab and throw so fast. I'm going to give you a specific clinical example about this in just a second. So in this particular picture, what they're showing us, I have a graph here. Let's not worry about the graph. It usually causes confusion. We have a transporter here carrying the little yellow molecules across the membrane. And we see that as the concentration of the molecule gets bigger and bigger and bigger, these transporters are able to transport more and more across the membrane just because there's more of them. There will come a point in time, or there can, I should say, I don't say there will, but there can come a point in time to where there's so many molecules out here that need to be transported that they just simply can't. These guys, these receptors, cannot transport them fast enough, and so they just kind of build up, and they just kind of have to wait. It's like a little log jam that occurs. That's what saturation is. So let's just put a number here. Let's say that these transporters can move 1,000 molecules every single second. And at the end of 1 second, if there were 500 of them there, they'd all move across the membrane, right? Well, let's say there were 10,000 molecules there. And at the end of 1 second, 1,000 would get through, but then what happens to the other 9,000? They have to sit and wait. We've saturated the transporters. Or if I hired you for a job, and you can move 10 boxes into my office in 1 minute, and all of a sudden the UPS guy comes and he's starting to throw 20 boxes outside my office every minute, are you going to get all those boxes in my office at the end of 1 minute if all you can move is 10 a minute? Aren't they going to start to pile up in my hallway? I've saturated you. The UPS guy saturated you. And so it builds up, it builds up, it builds up. What does that have to do with anything clinical? I'll give you a specific clinical scenario where this actually happens. So let's talk about saturation here. The kidneys and diabetes. So diabetes mellitus, either type 1 or type 2, we'll talk about it in detail next semester. Do most of us know what diabetes is? Okay, diabetes mellitus, that is. There's other kinds of diabetes. But diabetes mellitus is the one that has to do with a blood glucose problem, an insulin problem. Either we don't make it, or the receptors for insulin are desensitized. All right? Bottom line is, if you don't treat diabetes, you are going to get a buildup of glucose in your body. What will you see if you took some tests on a patient? This is a kidney. Okay? Now, we're going to talk about how the kidneys work in a crap load of detail next semester. For right now, we're just going to keep it really, 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 really simple. As we're not treating diabetes mellitus, so this is untreated, I'll just call it diabetes. Either type 1 or type 2, doesn't matter. the patient's not treating it properly. This is all about saturation, by the way. Okay, saturation of the transporter, that's the blood. The job of the kidneys, again, we're going to keep this really, really simple, is to take glucose, which made its way into the kidney. I'll explain how that happens next semester. Glucose is to be transported via a transporter into the blood. And under normal conditions, glucose does not build up into our bodies to the point to where these transporters have any problem moving every bit of glucose into the blood. Now, if the kidneys don't move all of the glucose in the blood, or whatever the kidneys don't move into the blood, we'll end up where? What do the kidneys make when they filter your blood? They make urine. By the way, your urine used to be plasma, just so you know. Filtered plasma is what it is. So there's urine. Urine is stuff the kidneys took out of your plasma because we didn't want it, or need it. So if glucose is allowed to build up, because we're not treating our diabetes properly, what we will do is we will saturate those transporters. And now the transporter cannot get all of the glucose into the blood. Well, now it's going to sit in the kidney, but it's not going to sit in the kidney. Where's it going to end up? In your urine. There should be no glucose in your urine, or there can be trace amounts, but for the most part, it's considered none. If you have glucose dumped into your urine, that's what happened. Okay? Or at least as far as we know right now. All right? So this is a specific scenario where saturation can be measured. You just dip the urine, you look for urine, send it to a lab, they'll tell you that there's glucose in the urine. Okay? You with me? Yes? Yes.
As far as for facilitated diffusion, if you say it grabs and throws the different, substances that move through it, why wouldn't that require energy?
It doesn't. This is a passive transport mechanism.
I understand that, but why? I mean, if you say changes conformation to adjust the shape of what goes through it, wouldn't that require energy of some sorts?
There are things that the proteins are doing that are very biochemical, that are beyond this course. You'll probably talk about it in biochemistry, kinetics, all thermodynamics, a whole bunch of stuff. Is energy needed? Yes, there is some energy demand there. Is it needed by, is ATP directly doing it? It's not, but there are ways these proteins kind of work that, no, energy is not technically required. Okay? And kind of like a little reflexive type of a thing, like a praying mantis, you boom, boom, it just grabs it away. That's a good way to explain it. Okay? Do we need a gradient, by the way? Don't forget about the gradients. Right, so passive diffusion. All right? Are we good with saturation? And by the way, no matter what transporter we talk about, saturation holds true. You saturate transporters, no matter what kind we are. All right? Okay, now what? Now let's go to active transport. Let's finally talk about transport mechanisms that require ATP. These are the active transport mechanisms we're going to talk about. We're just going to take them right in order. The first one we're going to talk about is primary active transport. Again, ATP is required. Regardless of which of these transport mechanisms we're talking about, ATP is going to be required. So, let's first talk about primary active transport. Here's a picture showing what's happening. We're going to draw it. Now, there's a bunch of these primary active transporters in the body. I have listed two here. The sodium-potassium pump and the hydrogen-potassium pump. This is the one I'm going to spend some time on that I'd like you to know. We'll talk about this one next semester. I'll talk about another one later on this semester. There are bunches of others. We'll talk about a handful of them over the next 2 semesters. But the one that I want you to know for now is the sodium-potassium pump. I promise you the hydrogen-potassium pump won't be on this exam. It will be next semester. So, the sodium-potassium pump is telling you what it's moving. It's moving sodium and potassium. And this particular transporter, this pump, is ubiquitous, meaning it's everywhere. It's pretty much in every cell of your body. There are 40 trillion cells in your body, and this transporter resides